Welcome to all of you today. Now we discuss about the answer of MCQ 2021 Group A Biomathematics. 2021 DSE-A1 paper Group A. Answer the following multiple choice question with only one correct option. Choose the correct option with proper justification. First question is equilibrium point is 30 of the following two-dimensional model dxdt x1 minus x by 3 minus xy divided equal to x minus y1 into y is stable node, unstable node, locally asymptotically stable, none of these. So answer is the unstable node because first we suppose dxdt equal to fxy and dydt equal to gxy. So fxy equal to x into 1 minus x by 3 minus xy and gxy equal to x minus y into y. So del f del x, del f del y, del g del x, del g del y. And so the Jacobian j equal to fx fy gx gy and compute the Jacobian. Now here, given that 30 is the equilibrium point, so we now find the value of Jacobian matrix at the point 30. So if 30 equal to 0, g30 equal to 0. So 30 is an equilibrium point. Now j at the point 30 is the matrix -1 -3 0 2. So delta equal to -2 negative, d is the trace of j, which is also positive 1, and d discriminant t square minus 4 delta equal to 9 positive. So eigenvalues λ1 λ2 equal to t plus minus root d by 2. So eigenvalues are 1 positive and 1 negative, 2 and -1. Now λ1 equal to -1 less than 2 less than λ2. So the eigenvalues are reals and opposite signs, and the equilibrium point 30 is an unstable saddle point. So the answer of the question 1 is unstable saddle point. Next question, question 2. Question B, the Halling type 3 functional response phi n represent in n phi n plane a sigmoidal curve, option 2 a closed curve, option 3 a hyperbolic curve, option 4 a straight line. Now answer is Halling type 3 functional response. Answer is 1 sigmoidal curve, because the functional response phi n given by phi n equal to a n square by 1 plus age into n square. A is the searching rate and age is the handling time, and A is the pre-density and phi n is the pre-consumption rate. Since the curve of phi n in n phi n plane is a sigmoidal curve, that is a set curve, so it is known as sigmoidal response function. And the curve is this type. This is the phi n. Horizontal axis is n-axis and vertical axis is phi n-axis, and this is the phi n curve. So this is the answer. Question B is the sigmoidal curve, option 1. Next question, C. In Gompertz growth model, dPdt equal to Cp ln k by p, the population P grows fastest when P is equal to option 1 0, option 2 k, option 3 e by k, option 4 k by e, c and k being the positive parameters. So here the question, population P grows fastest. Now the answer is k by e. option 4. Next question, option C. Question 1C, Gompach growth model, dPdt equal to Cp ln k by p. Answer is 4 k by e. First, let Ap dPdt equal to Ap. So Ap equal to Cp ln means log to the base e k by p. For equilibrium point, dPdt equal to 0 gives Ap equal to 0. This implies ln k by p equal to 0. So obviously p equal to k, and this p are not equal to 0. Because if p equal to 0, then the model is undefined. So unique equilibrium point is the p star equal to k. Here p is greater than 0, and because the p not equal to 0, because the model is undefined for p equal to 0. Now we find dPdt is equal to c into p ln 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 k minus ln p. And next second derivative d2p dt square, that is equal to c ln k dPdt, and this is this. So c square p ln k by p ln k by p minus 1. Now second derivative equal to 0 implies that ln k by p equal to 0 or ln k by p minus 1 equal to 0. Now ln k by p equal to 0 means the ln equal to ln 1. So k by p equal to 1, that is p equal to k. And from ln k by p minus 1, we get 1 equal to ln e. So k by p equal to e, and so p equal to k by e. So we get two values of p when d2p dt square equal to 0, p equal to k or p equal to k by e. But p equal to k is an equilibrium point. So dPdt at the point p equal to k equal to 0. So for p equal to k, growth rate is 0, because dPdt equal to 0. dPdt means the growth rate of p. So now for p equal to k by e, here we get two cases when p lies between 0 and k by e, that is 0 less than e less than k by p. So taking log to the base e, ln 0 less than ln e less than ln k by p, that is minus infinity less than 1 less than ln k by p. And so d2p dt square equal to c square p ln k by p into ln k by p minus 1, obviously greater than 0, because ln k by p is positive. Here ln k by p is positive, greater than 1. So this is this c square positive, p positive, ln k by p positive, k and p both a positive quantity. So ln k by p greater than 1. So ln k by p minus 1 is obviously positive. So d2p dt square is positive. So when p lies between 0 and k by e, we get second derivative of p is positive. On case 2, when p lies k by e less than p less than k, and then k by p less than e less than k by p. And so ln k by p less than ln e less than ln k by p. So ln equal to 1, so ln k by p less than 1 less than ln k by p. So d2p square equal to this and this negative, because ln k by p is less than 1. So p is less than k and 1 is less than k by p. ln 1 is less than ln k by p, that is ln 1 is log to the base e1 equal to 0. So 0 less than ln k by p. So this ln k by p is positive, and ln k by p minus 1 is negative. So d2p dt square is negative when p lies between k by e and k. Thus, we get this the graph. The horizontal axis is t-axis, the time axis, and the vertical axis is p-axis, the density of population, and this k is carrying capacity, and this point k by e, and this graph of p times the solution with respect to t. And so at this point k by e, this p double dash equal to 0, second order derivative 0 for p equal to k by e. And between 0 to k by e is p second derivative is negative, and when k by p is lies between k by e to k, then p double dash is greater than 0. So here k by e is a point of inflection, and point of inflection. So the consequently p grows fastest when p equal to k by e, and the growth rate is dn dt at the point p k by e is the ck by e is the fastest growth rate for this point. So this is the point of inflection. P equal to k by e is the p grows fastest when p equal to k by e. Next question. Uh, Question D, what type of bifurcation will occur in the system dxdt equal to mu x minus x cube, where mu is the bifurcation parameter? Option 1, saddle node bifurcation, option 2, pitchfork bifurcation, option 3, transcritical bifurcation, and option 4, none of these. Now, in this question D, answer is the pitchfork bifurcation. This type of differential equation dx equal to mu x minus x cube is the pitchfork bifurcation, because uh, dx equal to 0 for the equilibrium point, so we get the values of x equal to 0 or root mu or minus root mu. So we get three equilibrium points: x1 star 0, x2 star equal to minus root mu, x3 star equal to root mu. And dx dt equal to mu x minus x cube equal to fxa. So df dx equal to mu minus 3x square. So df dx at the point x1 star equal to mu, df dx at the point x2 star equal to minus 2 mu, and df dx at the point x3 star equal to minus 2 mu. If case 1, if mu is negative, then x equal to plus minus root mu are complex numbers, obviously. So we get the only one equilibrium point x star equal to 0, and df dx at the point x star equal to 0 equal to mu, and mu is negative, so x star equal to 0 is a stable equilibrium point when mu is negative. And case 2, when mu greater than 0, then we get three equilibrium points: x1 star 0, x2 star minus root mu, x3 star equal to root mu. And df dx at the point x1 star is mu positive, so x1 star is unstable equilibrium point. Df dx x2 star equal to minus 2 mu negative, so x2 star is x2 star equal to plus or minus root mu. In both cases, df dx equal to minus 2 mu, and mu is positive, so obviously minus 2 is negative. So x2 star equal to minus root mu and x3 star equal to root mu are both stable equilibrium points. And so we get this graph of this x phase portrait of this x and dx dt dx dt equal to this stable equilibrium point when mu is less than 0. So only one equilibrium point and which is stable. And when mu equal to 0, we will also get one equilibrium point is 0, x equal to 0, x star equal to 0. And when mu is positive, we get three equilibrium points: this x star equal to 0, and x2 star equal to root mu, and x3 star equal to minus root mu. And 0 is unstable, and root mu plus minus root mu is stable when mu is greater than 0. And we draw the mu and x plane. The mu is the horizontal axis and vertical axis is x axis. So stable, this when mu is negative, so this is the stable equilibrium point, and this is the only one equilibrium point 0. So x equal to 0, and which is stable equilibrium point when mu is negative. And after that, when mu is positive, we get two equilibrium points, root mu and minus root mu, and 0 is the unstable equilibrium point. So we draw here dotted line, dashed line, and this is the solid line for this curve. So this is the supercritical pitch for bipercussion. Bipercussion 0, is the mu explained. An exchange of stabilities takes place between the equilibrium points. This type of bipercussion is known as pitch for bipercussion. Next question. Next question. Question E. A two-dimensional system has characteristic equation lambda square minus alpha lambda plus alpha beta 1 minus alpha equal to 0, where alpha greater than 0, beta greater than 0, and equilibrium point alpha 1 minus alpha. If 4 beta by 1 plus 4 beta less than alpha less than 1, then equilibrium is number 1 unstable focus, number 2 unstable node, number 3 stable focus, number 4 stable node. Here, answer is 4 stable node. Now, Raut Hargwich criteria, this lambda square plus A1 lambda plus A2 equal to 0, and all roots have the real lambda is negative, and if and only A1 is positive and A2 is positive. This is the Raut Hargwich criteria for a quadratic equation. A real lambda less than 0 implies that the stable equilibrium point exists. And when now alpha greater than 0 and alpha beta bracket 1 minus alpha greater than 0, and then this implies 1 minus alpha greater than 0, so alpha is less than 1. The question, this question, alpha greater than 0, beta greater than 0. So alpha beta 1 minus, because here a1 is this, a1 is alpha, and a2 equal to alpha beta into bracket 1 minus alpha. So for stability, A1 positive and A2 positive, so obviously we get alpha greater than 0 and alpha beta into 1 minus alpha greater than 0. So alpha is negative. Thus, equilibrium point is stable. Equilibrium point means this here equilibrium point alpha, comma 1 minus alpha is the equilibrium point. So equilibrium point is stable equilibrium point if alpha is negative, less than 1. And note that this alpha beta always positive, greater than 0 both. Now discriminant d of the given equation is this alpha square minus 4 alpha beta into 1 minus alpha. So discriminant is, after simplification, alpha into 1 plus 4 beta bracket alpha minus 4 beta by 1 plus 4 beta. And if alpha minus 4 beta by 1 plus 4 beta is positive, that is if alpha is greater than this, then d is positive. So we get a real and distinct eigenvalues, and so we get node, distinct eigenvalues, so we get node. Thus for 4 beta by 1 plus 4 beta less than alpha less than 1, equilibrium point alpha 1 minus alpha is a stable node, because this condition is alpha is less than 1 and 4 beta by 1 plus 4 beta is less than alpha, so we get stable node. Next question F. If in the two-dimensional system dx dt equal to 2 minus x plus x square by y, dy dt minus x cube equal to x cube minus y, x is an activator of y and y is inhibitor of x, y is activator of x is inhibitor of y, both of them are activator inhibitor, none of this. Now this question is the out of syllabus in the revised syllabus, according to the revised syllabus effect from the 2022. So the question is the out of syllabus, but we give here answer. Option 1, x is activator of y and y is inhibitor of x. Because we know for general system dx dt equal to fxy and dy equal to gxy, X is activator of Y if del G del X is positive, and Y is an inhibitor of X if del F del Y is negative. Now here F is this and G this, so find del F del X, del G del X, del F del Y, del G del Y, and clearly del G del X is 3x square. So obviously 3x square is positive, and so X is activator, and del F del Y equal to minus x square by Y, obviously this is negative, so Y is an inhibitor of this. But this question is about is out of syllabus. Question G, the equilibrium point x equal to k for the equation dx dt equal to rx1 minus x by k whole to the power theta. R, k, theta are positive parameters. Option 1 unstable, option 2 stable, option 3 stable but not asymptotically stable, none of this. Now here answer is this. Answer is answer is 2 stable. Answer is stable because dx dt equal to fx, where fx equal to rx bracket 1 minus x by k whole to the power theta, and this, and now we find the f dash x, and this r minus r by k to the power theta, theta plus 1 x to the power theta. When x equal to k, and f dash k equal to this equal to minus r theta, and r and theta are both positive, so minus r theta is negative, so f dash k is negative, so x star equal to k is an asymptotically stable equilibrium point. X star equal to k is asymptotically stable equilibrium point. So answer is this stable, as option 2, answer is stable equilibrium point. Next, question H. Consider a dynamical system dRdt equal to r bracket 1 minus r minus 2, r minus 3, and d theta equal to 1, where r theta polar coordinates on the plane. The number of limit cycles is option 1, 1, option 2, 2, option 3, 3, and option 4, 4. This option answer is this option, these 3. 3 limit cycles. Now dRdt equal to 0 implies r equal to 0, r equal to 1, r equal to 2, r equal to 3. And d theta dt equal to 1 gives the anticlockwise is positive, so this is the anticlockwise rotation of this periodic orbit. Now r equal to 0 is not a periodic solution nor a limit cycle, so r equal to 0 corresponds with the origin, because this when 0 less than r less than 1, dr dt is positive, because dr dt equal to r into 1 minus r minus 2, r minus 3. So when r lies between 0 and 1, so r is positive, 1 minus r is positive, r minus 2 is negative, r minus 3 is negative. So negative, negative, positive, so dr dt is positive. So dr dt positive means r is the increasing function with time t. So r moves away from the origin and going to r equal to 1, going to r equal to 1. So r equal to 0 is the unstable equilibrium point. And when r lies between 1 and 2, when r lies between 1 and 2, dr dt, so r is positive, 1 minus r is negative, r minus 2 is negative, r minus 3 is negative. So dr dt is negative. So r is decreasing function with time t. So r moves inwards direction. Inward direction means in this region, so r equal to 1 in this circle, this, and r equal to is the outer circle. So when lies between r lies between these, so r moves towards this r equal to 1 cycle, r equal to 1 cycle, r equal to 1 cycle. So and r equal to 1, that means x square plus y square equal to 1. This circle is stable limit cycle. This stable limit cycle, stable limit cycle, and this the because and this origin is unstable equilibrium point. So trajectories goes goes towards the r equal to 1 in the inside of the circle, and outside region when r lies between r equal to 1 and r equal to 2, and then these trajectories goes to the circle r equal to 1. So r equal to 1 is the stable limit cycle, and we draw this stable limit cycle in green circle, is green circle. And next, when r lies between 2 and 3, d at dt is positive because r is positive, 1 minus r is negative, r minus 2 is positive, r minus 3 is negative. So d at dt positive, so r is increasing with t, so r moves away from r equal to 2 cycle and moves towards the r equal to 3 cycle. So this outer circle is r equal to 3 and inner circle is r equal to 2. So r moves away from r equal to 2 and moves towards r equal to 3 cycle. So r equal to 2 is an unstable limit cycle, And when r is greater than 3, we get r is positive, 1 minus r is negative, r minus 2 is positive, r minus 3 is positive. So d at dt is negative. So r is decreasing function with time t. So r moves towards r equal to 3, and so outer region of r equal to 3, and in this region the trajectories go to the circle r equal to 3. So r equal to 3 is a stable limit cycle. So we get 3 limit cycles r equal to 1, stable limit cycle r equal to 2, unstable limit cycle, and r equal to 3 is a stable limit cycle. Next question, the fixed point x star equal to alpha minus 1 by beta of the difference equation x n plus 1 equal to alpha xn by 1 plus beta xn when alpha is greater than 1, beta is greater than 0 is option 1 unstable, option 2 asymptotically stable, option 3 stable but not asymptotically stable, option 4 none of these. The answer is this, this the asymptotically stable. Perhaps the answer is this, for this asymptotically stable. Yes, option answer is asymptotically stable. Explanation for this question, here xn plus 1 equal to alpha xn by 1 plus beta xn, and this right hand side function is call it f of xn. So xn plus 1 equal to f of xn, where f of xn is alpha xn by 1 plus beta xn. And so we can write omit the suffix n, so we can write fx equal to alpha x by 1 plus beta x, and then f dash x equal to alpha by 1 plus beta x whole square. Now this is the equilibrium point alpha minus 1 by beta, so f dash x for this equilibrium point x star equal to this, and this 1 by alpha, beta beta cancel, and minus 1 minus 1 cancel, and alpha square alpha by alpha square, so 1 by alpha, and this is less than 1, and this is less than 1 because alpha is greater than 1, so 1 by alpha is less than 1, so alpha if dash x star is 1 by alpha is less than 1. We know that if a modulus value of f dash x star is less than 1, then x star is an locally asymptotic equilibrium point for xn plus 1 equal to fxn. So obviously alpha minus 1 by beta obviously asymptotically stable equilibrium point. Next question. Square and dy dt equal to x plus y into this, and this the has no closed orbit inside the circle, x square plus y square equal to 1, and x square plus y square equal to 2, x square plus y square equal to half, x square plus y square equal to 1 by 4, has no closed orbit inside the circle. So here answer maybe 3, maybe 4, maybe 1. So this question, this the system, no closed orbit, option 1, 3, and 4. First we write the in the form of limit cycle, x equal to r cos theta, y equal to r sin theta, and we get the corresponding polar form of the system is dt equal to r into r square minus 1 and d theta equal to 1. And dt equal to 0 gives r equal to 0 and r equal to 1. Here r is positive, so r not equal to minus 1. And when 0 less than or less than 1, dt is negative. So r is decreasing with time t and r move towards r equal to 0. Then r equal to 0 is stable equilibrium point. When 1 is less than r, r is greater than 1, so dt is positive. So r is increasing, r greater than 1, that is r increasing, so r moves away from r equal to 1. So r equal to 1 is a unstable limit cycle, and so this is this. So clearly, there is no closed orbit within the r equal to 1. So r equal to 1, no closed orbit r equal to 1, that is x square plus y square equal to 1, no closed orbit. And alternatively, we can derive this condition Bendixson negative criteria. Here dx equal to pxy, dy equal to qxy, where pxy equal to this function and qxy equal to this function. Now, del p del x equal to this and del q del x equal to this. Now we know this del p del x plus del q del y, when maintain the same sign, either positive or negative throughout the region. So then the no limit cycle. Here del p del x plus del q del y equal to 4 into this this negative when x square plus y square is half, less than half. Then this is negative throughout a region. In the region x square plus y square less than half or x square plus y square less than 1 by 4, this del p del x del q del q del y is negative. So by Bendixson criteria, negative criteria has the same sign for this. So in this region, x square plus y square less than half or x square plus y square less than 4, there is no closed orbit inside the circle. So your answer is three answers, either 1 or 3 x square plus y square equal to half, or 4 x square plus y square equal to 4. Thank you, all of you. This is the all answers of the multiple choice question of 2021 question paper. Thank you.